Imagine a bubble in space, one that expands faster than light, carrying with it a force so devastating it literally erases everything in its path, all without you ever feeling a thing. Sounds like science fiction, right? Well, it's not. It's cosmology. And in today's video, I want to tell you about the false vacuum bubble of doom. We think of empty space as, well, nothing, but that's only because we're not standing next to anything. In fact, it's filled with particles popping in and out of existence. This is called the quantum foam. So when we say there's nothing in space, we mean there's nothing there that we can measure. Space is filled with this particle soup, but those particles have a problem. They're massless, which is great for traveling through the universe, but terrible for maintaining a long-term relationship. Since they have no mass, they don't stick together. We can't form molecules, and without molecules, we can't form stuff. So in order for the world as we know it to exist, most of these particles need to have mass. That's where the Higgs field comes in. The Higgs field is an invisible energy field that fills all of space, kind of like the background hum of a TV set that everyone tuned out years ago. For some reason, almost every single particle interacts with the field, except photons. And how they interact gives them their mass. You might be wondering why it's called the Higgs field when we have been talking about it like it is a particle. Well, it is both. Really, it's just a way of describing how particles gain mass. But if you want to learn more about what the Higgs actually is, check out Minute Earth's video. Link below. The value of the Higgs field at any given point in space is measured by something called the condensate, which tells us how dense it is. And since we know the masses of various particles, we also know how strong they interact with the field. If the constant is high, then the particles will interact strongly with the field and have a large mass. If it's low, then they'll interact weakly and be lighter. The standard model of particle physics fits pretty well when we assume the constant is around 246 GeV, but that doesn't mean it has to be. It just means that that value of the constant results in particles with the masses we observe. And here's where things start to get weird. We believe the condensate could be slightly higher or lower than 246 GeV, maybe even much lower. If it were lower, the neutrons inside atomic nuclei would fly apart, but that hasn't happened, which sets an upper limit on how far it could be reduced. The upshot is that we live in what's called a metastable vacuum, a state that's relatively stable, but not the most stable possible state. There are other states, called true vacuums, that would be lower energy and thus more stable. But how do we get from here to there? To understand that, we need to look at the mathematics of quantum mechanics, specifically something called quantum tunneling. Imagine you're trying to roll a ball over a hill. Classically, if the ball doesn't have enough energy to get over the hill, it'll just turn around and go back where it came from. But quantum mechanically, there's a small chance it can just go through the hill. In fact, there's always a small chance a ball can tunnel through any energy barrier. But here's the crazy part. Inside the ball, while it's going through the hill, it experiences a region of lower energy. This is analogous to our current vacuum state. If the ball represents our universe, then rolling it down the opposite side of the hill represents transitioning to a true vacuum. Once it's there, it's not going to come back. And in fact, once quantum tunneling kicks in, the likelihood of returning to the original state goes to zero exponentially. It's worth noting that this process is purely probabilistic. All we can ever talk about is the likelihood of tunneling occurring. Just because we can't measure the probability of the universe tunneling to a true vacuum doesn't mean it is impossible. It's possible that it will never happen. But it's also possible that it happens in less than 1 trillion years. And since the universe is only about 13.8 billion years old, that means it's likely to happen again, but not before a very, very long time. Now, you might think that tunneling is just some mathematical curiosity. After all, we never see macroscopic objects tunneling through energy barriers. But it's really just the mathematical manifestation of a physical process that's happening all the time. Whenever a particle hops over an energy barrier, it tunnels. And since tunneling can't be switched off, it's always happening somewhere in the universe. This raises the question, could a bubble of true vacuum spontaneously nucleate inside the metastable vacuum we inhabit? And if so, how long would it take? A team of physicists from the Czech Republic and the US looked at the question from both the inside and outside of the bubble. Here's what they found. First, let's talk about what it's like inside the bubble. According to Einstein's theory of general relativity, as the bubble expands, it does so at nearly the speed of light. Why almost? Because nothing can travel quite that fast. But general relativity says that the bubble wall itself travels at light speed. So the interior of the bubble moves away from the wall at almost the speed of light. And this creates a Doppler shift that slows the bubble wall down a bit relative to the overall interior. As the bubble expands, it drags the particles of the quantum foam along with it, but those particles aren't free. The bubble wall carries a lot of energy and exerts a pressure on anything that gets too close. So if you wanted to escape, you'd have to find a way around the wall, which is impossible. Once a bubble is formed, its internal structure is frozen in time. Inside the bubble, the true vacuum is not only more stable, it's also featureless. Most importantly, the constants of nature are different. We wouldn't recognize the laws of physics. We can't really imagine what would happen to organic molecules, but clearly no chemistry would work the same. At the very least, we'd need to rewrite biochemistry. But even if life still somehow exists, it would evolve differently, because the fundamental constants of nature would no longer be the same. So what would it be like outside the bubble? As the bubble begins to expand, the inside races away from the wall at nearly the speed of light. This makes the interior appear blue-shifted, meaning its light gets squished to shorter wavelengths. Eventually, however, the wavelength gets so small that it falls out of the range of what we can detect. In other words, you'd never see the bubble coming. In fact, there's no way to detect the approach of a bubble until it is already here, because the only evidence of its arrival would be light from the inside that got stretched by the expanding bubble wall. And by the time you saw it, the bubble would already be expanding at nearly the speed of light. If you could see the entire bubble, it would look like a bright line moving away from you at nearly the speed of light. And after you saw it, you wouldn't see anything else. Why? Because the moment the bubble touches you, it kills you. As the bubble wall passes through you, it squeezes the particles of the quantum foam into a different energy state. Since this process is irreversible, your body can't maintain its structure and falls apart. And it doesn't just happen to your body, it happens to everything. The bubble wall annihilates everything in its path. And here's the kicker, there's no way to escape. Since the bubble wall is moving at nearly the speed of light, there's nowhere for you to run. You can't move faster than light. It's physically impossible. The only thing you could do is watch the bubble arrive and kill everything you've ever known and loved. But wait, you might say, if it kills everything, then how are we talking about it right now? Well, here's where the skeptics come in. They point out that the bubble is moving at nearly the speed of light and therefore requires an immense amount of energy. In fact, the wall itself has a huge amount of energy per unit volume, about 10 to the 10 gigabits per cubic meter. But the thing is, that's assuming the bubble stays intact. What if new physics steps in and stabilizes the metastable vacuum instead? Maybe the bubble doesn't expand at all. Or maybe it stops growing when it hits a planet and gets absorbed. The point is, we just don't know. And that leads us to another problem. If the bubble destroys everything inside, how can we gather data to constrain the model? The answer is, we can't. We can only use what we observe now to estimate the likelihood of it happening in the future. To make matters worse, the bubble could create gravitational waves as it expands. And if we detect those, we'll know that the end is near. But those waves would also carry away energy that could slow the bubble down. So any constraint we place on the rate of expansion would depend on the strength of yet unknown physics. All in all, the bubble may seem like an academic exercise, but it highlights some important points about the limitations of physics. There's a lot we don't know about the laws of nature. And although we have a good idea of what's likely to happen in the future, there are always possibilities that we haven't considered. But okay, enough of that. Time for the mini quiz I promised. Question: if the bubble of doom began expanding towards Earth, which would arrive first? The news that the bubble is coming, or the bubble itself? Pause the video here if you want to make a guess. Okay, the answer is the bubble itself.